Welcome back. In this video, we are going to solve problem 6-67 and 6-68, and this is from chapter number 6, Bending, and book name is Mechanics of Material by R.C. Hibbeler. So let's start with the 6-67. The statement is the shaft is supported by smooth journal bearing at A and B that only exert vertical reaction on the shaft. If D is equal to 90 millimeter, determine the absolute maximum bending stress in the beam. Sketch this stress distribution acting over the cross section. So you can see this is beam that is made up of shaft, and there are two general bearing at A and B that exert vertical reaction. The load is shown from A to B. There is a uniformly distributed load of 12 kilonewton per meter, and from B till end there is a uniformly decreasing load or triangular load. So diameter is also given, that is 90 millimeter. So you have to find the absolute maximum bending stress, and then you have to show the stress distribution over this cross section. So let's start with the solution. So first step is that if you remove this general bearing at point A, so there will be a reaction force exerted by general bearing on this shaft, which is RA, and similarly if you remove this general bearing at B, so there will be reaction force RB. So first we will find this RA and RB by using equation of equilibrium. Now you can see from A to B there is a uniformly distributed load of 12 kilonewton per meter. So when converted it into a point load, it will be equal to 12 over the length over which it acts, that is 3, and that is 36 kilonewton. And that will act at the half of, at the mid, which means that this will be 3 meter. 1.3 divided by 2, which is 1.5 meter, and this remaining will be also 1.5 meter. Similarly, you can see you have triangular load, so when you convert it into a point load, so it will be equal to 1 over 2 into this 12, and the length is 1.5. So that will give you 9 kilonewton, and that will act at a length of L by 3. So L is here 1.5. Here this is 1.5 divided by 3, which is equal to 0.5 meter, and this remaining will be 1 meter. Okay, now we'll apply equation of equilibrium. So first equation of equilibrium is that sum of all the moments about point A is equal to 0, and taking the counterclockwise moment as positive. So about this point A, the first moment will be this load, which is 36, and perpendicular distance is 1.5, and this is clockwise, so it will be negative. So I will write it first. This 36 into perpendicular distance is 1.5, and this will be minus. The second moment will be due to this RB, and perpendicular distance is 3, and this is counterclockwise movement, so it will be positive. So I will write plus RB into 3. The third moment will be produced due to this load, which is 9 kilonewton, and now perpendicular distance is 1.3 plus 1.3 plus 0.5, which is 3.5, and that is clockwise, so it will be negative. So I will write minus 9 into 3.5 is equal to 0. So again, when you calculate this, and you will get RB is equal to 28.5 kilonewton. This is the value of RB. Clear? Now we'll find RA by using equation of equilibrium, that sum of all forces along y direction must be equal to 0, and upward force is taken as positive. So RA is upward, so RA, this 36 is downward, minus 36, this 9 is also downward, minus 9, plus this RB, which is 28.5, is equal to 0. So from here RA will be equal to RA will be equal to 16.5 kilonewton. Now you have both RA and RB, so we will move to draw the shear force and bending moment diagram. For that I have to draw the vertical line from the end of the beam. Clear? And we will draw the shear force and bending moment diagram. Okay, so here we will take a horizontal line to show length x in meter. On y-axis we have shear force that will be in kilonewton. Let each division is 5. So 5, 10, minus 15, plus 15, plus 20. Similarly, minus 5, minus 10, minus 15, and minus 20. Okay. So at point A, you can see you have RA, which is 16.5. So first point will be 16.5. Let this is 16.5 kilonewton. Now at point B, this is the point, this is length of 3 meter, clear, 3 meter. Now at 3 meter, we have, at this point, we have, at there is a uniformly distributed load over a length of 3 meter, so it is 36. So at this point load will be equal to 16.5 minus 36, and that will be equal to minus 19.5. So we will locate minus 19.5. So 19.5 will be somewhere here. This will be 19 point minus 19.5. Now you can see that this load is a horizontal load with a 0 degree, so shear force will be 1 degree higher, and this load is downward, so slope will be decreasing. It will be a first degree line and slope will be decreasing. It will be straight line joining these 2 points. Let me join it again. Let me join it by using ruler. Okay, so I will join them by using this ruler. Okay, I don't know why I am facing difficulty today. Okay, let me try like this. It will be a straight line joining these 2 points. Okay, now you can see that I have joined these 2 points, clear, and at this point we have RB upward, which is equal to 28.5. So minus 19.5 plus 28.5 will give you 9, plus 9. So at this point shear force will change to plus 9. Let this is plus 9. So shear force will change to plus 9. And here you can see you have a uniformly decreasing load, so this will be equal to, that is, you can see that is 9, and that will be downward, so it will be minus 9. So plus 9 minus 9 will bring it to 0 at this point. And you can see that this load is a 1 degree line and slope is decreasing, so bending, so its shear force will be a second degree curve, and it will be like this. Clear? It will be like curve, not a straight line, but it will be like a curve. So this will be your shear force diagram. Now at this point you can see we have shear force is 0, and at this point the bending moment will be maximum. So for that we will find this x. So for x we will cut this beam at any length x, and we'll draw the free body diagram of this beam. So this is RA, which is 16.5. This is the length X over which we cut this beam, and there is a uniformly distributed load which is equal to 12 kilonewton per meter. There will be a shear force, clear, and this shear force will be there, and there will be a bending moment. So we will find the equation of shear force. Now you can see this, when this uniformly distributed load is converted into point load, so it will be equal to 12 into the length over which it acts, and that is x, and that will act at a distance of x by 2 at half of this length. So this will be x by 2 and this will be x by 2. Now we'll find this shear force equation by using sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So you can see 16.5 which is acting upward minus this 12x that load is downward, and this minus v is equal to 0. So from here this v will be equal to 16.5 minus 12x. If you put x is equal to 0, so you can see that shear force at x will be equal to only 16.5. Okay, now we are going to find the value of x for which shear force is equal to 0. So put v is equal to 0. So 0 is equal to 16.5 minus 12x, and 12x is equal to 16.5. So x will be equal to 1.375 meter. Clear? So this is the length at which x is equal to 1.375 meter, at which we have shear force is equal to 0. Now we'll draw the bending moment diagram. So for that I have to draw a vertical line from the end of this beam, a horizontal line that will show x in meter, and on y-axis we have moment that will be kilonewton into meter. Let each division is 5, so 5, 10, 15, similarly minus 5, minus 10. Okay, the first area under the shear force diagram is this one, and this area, let this is A1, and this area A1 is equal to area of this, as this is triangle, so its area is equal to half into height into its width. So 16.5 and width is 1.375. So 16.5 multiplied by 1.375, and that will be equal to 11.34. So at this length we have 11.34. So let 11.34 is this point, 11.34 kilonewton into meter. Now you can see that shear force is a 1 degree line and its area is positive, and but slope is decreasing. So bending moment will be second degree curve and it will be clockwise. So we can join these 2 points by using, it will be a second degree curve there like this. Now the second area is this one, and this area A2 is equal, this is also triangular, so its area is equal to half of this width, which is equal to 3 minus 1.75. Clear? And height is this 11 19 point minus 19.5. So when you calculate it, you will get this area is minus 15.84. So 11.34 minus 15.84 will is equal to minus 4 at this point. So at this point the moment will be minus 4.50. 4.50 minus, and again this will be, you can see that shear force is a horizontal line with 1 degree. So bending moment will be second degree curve and slope is decreasing, so it will be again clockwise. So we will join these 2 points again like a curve. So it will be like this. Now the third area is this one, and you can see this area is E3, and this area will be equal to BH over 3 because this is parabolic spandrel, and its area is equal to BH by 3. So B is this one, which is 1.5, and H is 9. And when you calculate it, you will get this area will be equal to plus 4.50. So minus 4.50 plus 4.50 will bring it to 0. And you can see this is a second degree curve. So bending moment will be third degree, and it will be like this. It will be like this. Clear? So this is your bending moment diagram. Now from BMD, bending moment diagram, we can see that maximum bending moment is equal to 11.34 kilonewton into meter. So we know that maximum bending stress is equal to maximum bending moment into C divided by I. Diameter is given as 90 millimeter. So diameter is 90 millimeter. So radius C is equal to D divided by 2. So 90 divided by 2 is equal to 45 millimeter, and in meter it is equal to 0.045 meter. And what about JI? I, second moment of inertia of this circular shaft, it is equal to pi by 4 C power 4, and that is pi by 4 into 0.045 power 4. The unit will be meter power 4. So put this in this formula. Maximum bending moment, bending stress is equal to maximum bending moment, which is 11.34, and we will convert this kilonewton into 10 raised to power 3, multiply by C is 0.045, divide by I, which is pi by 4 into 0.045 power 4. So when you calculate it, you will get maximum bending moment is 158 into 10 raised to power 6 Pascal, Newton per square meter, that is Pascal. So 158 megapascal. This is maximum bending stress, which is the answer of our the first part of this question, which is question 6-67. Now we'll move to solve problem 6-68. And what's the statement? The statement is the shaft is supported by smooth journal bearing at A and B that will exert vertical reaction on the shaft. Determine smallest diameter D if allowable bending stress is 180 megapascal. So we have been given allowable bending stress, that is 180 megapascal. Okay. Now we know that maximum or allowable bending stress is equal to maximum bending moment into C divided by I. So we have to find the diameter for this allowable bending stress. C is not known. We have to find this. So we know that allowable bending stress is 180 megapascal. So 180 into 10 raised to power 6. Maximum bending moment, from this diagram you can see 11.34 kilonewton into meter. So 11.34 into 10 raised to power 3. C is equal to diameter divided by 2, and I is equal to pi by 4 C power 4, and C is D by 2 power 4. So from here you will get this will cut with one of this, so we will left with 180 into 10 raised to power 6 is equal to 11.34 into 10 raised to power 3 divided by pi by 4 d by 2 power 3. Clear? Now d by 2 power 3 will be equal to 11.34 into 10 raised to power 3 divided by pi by 4 into 180 multiplied by 10 raised to power 6. And when you solve this, this d cube will be equal to 8 multiplied by 11.34 into 10 raised to power 3 divided by pi by 4 into 180 into 10 raised to power 6. And this d power 3 will be equal to 0.0006169, and d cubic cube cubic square root will be equal to cubic square root 0.000641669, and from here you will get this d will be equal to 0.0862 meter, or this d will be equal to 86.3 millimeter, which is the answer of our second part. Remember, if you have been given problem 6-68, so you will need maximum bending moment, for which you have to perform all these things. Clear? Once you get maximum bending moment, so you can just put in this formula. Now, the last thing is that in part first, we have been asked to find the shear stress distribution over the cross section. So let me draw the cross section. If this is the cross section that is shown over here, for example, if this is the rod, clear, like this, and this is the center or neutral axis, so at this point we have maximum bending moment, which is this one, clear, and it will be like this, it will be like this. And similarly the same is the case for this one. You have maximum bending moment and it will be like this. Clear? So you can see on the top we have compression. Clear? You have to like this, and on bottom you have extension, tension. So this will be your stress distribution over the cross section. And that was all about this problem 6-67 and 6-68. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching.